talk about ordered fields. To do so, let's first recall the definition of a field. We say that a triple, a set F, along with addition plus and multiplication dot, is a field if it satisfies the following 10 axioms. First, we need to make sure that it's closed under addition and multiplication. Second, we need to have a few properties about addition. Given three elements x, y, and z, first, the order in which we add shouldn't matter. X plus y is y plus x. The grouping in which we do this should not matter. So we could either add x plus y and then add z, or we can add y plus z and then add x. There should be an element that we'll call 0, such that x plus 0 is x for all x. And for each x, there should be an element called negative x, its additive inverse, such that x plus its negative is this so-called 0 element. There are similar properties for multiplication. Given x, y, z, and f, the order of multiplication should not matter. So x times y is y times x. The grouping should not matter. So we can multiply x times y and then multiply by z, or multiply by y and z and then multiply by x. There should be a number that we'll call 1, that's our multiplicative identity, where x times 1 is x. And finally, there should be multiplicative inverses. To be more precise, if x is non-zero, then there is an element that we'll call x to the minus 1, such that x times x to the minus 1 is our multiplicative identity. The 10th axiom says that there should be a relationship between addition and multiplication. Given three elements x, y, and z, we can first add y and z and then multiply by x, or we could multiply x and y, multiply x and z, and then add those two resulting numbers together. The rational numbers, the real numbers, and the complex numbers are all examples of fields. Eventually, we'll come back and define the real numbers and the complex numbers, but keep in mind that these latter two are examples that we do want to deal with here for this course. Unfortunately, neither the natural numbers nor the integers is a field. The simple explanation is if you're given an integer such as the number 2, its multiplicative inverse, namely 1/2, is no longer an integer. In any field, we must have elements 0 and 1, and they must be distinct from each other. We'll play around with these quite a bit here in this course. Axioms F4 and F8 give the existence of an additive identity and multiplicative identity. Similarly, axioms F5 and F9 give the existence of additive inverses and multiplicative inverses. We've actually found that these are unique. In a field, the additive and multiplicative identities are unique. Similarly, the additive and multiplicative inverses are unique. We're going to use all of these properties now to try to define an ordered field. Let's say that F is a field. Given a subset P, we may define an order relation by saying x is greater than y whenever the difference, x minus y, is in P. Intuitively, we're going to think of P as the positive elements in F. We say that our field, along with this set P, is an ordered field if the following three properties hold. First, axiom O1 is our trichotomy property. Given an element x in F, exactly one of three properties holds. Either x is 0, x is positive, or x is negative. To be more precise, we're saying either x is equal to 0, x is an element of P, or negative x is an element of P. Second, if we're given two positive elements, x and y, then their sum is also positive. To be more precise, whenever x and y are elements of P, the sum x plus y is also an element of P. And finally, the same should be true for products. That is, if x and y are positive, then its product, x times y, is positive. To be more precise, whenever x and y are in P, x times y is also in P. Both the rational numbers and the real numbers are examples of ordered fields. In this case, we can just let P be the collection of positive elements. Indeed, it should make sense that the sum of two positive rational numbers is positive, and the product of two positive rational numbers is positive. On the other hand, the complex numbers do not form an ordered field. We'll come back and we'll see in a bit more detail as this course goes on why this case is not true. Given an ordered field, remember that we'll say that x is less than y whenever y minus x is positive. We'll use this to define an absolute value. Using the trichotomy law, we'll define the absolute value of a number x as follows. The absolute value of x is 0 if x is 0. The absolute value is x if x is positive, and the absolute value is negative x if x is negative. We have three important properties based on this definition. First, for any x in f, its absolute value is greater than or equal to 0. Moreover, the absolute value of a number x is 0 if and only if x itself is 0. Second, the absolute value is multiplicative. That is, given any elements a and b in f, the absolute value of its product is the product of the absolute values. That is, the absolute value of a times b is the absolute value of a times the absolute value of b. We also have what's called the triangle inequality. That is, given any two elements a and b in f, the absolute value of the sum is less than or equal to the sum of the absolute values. That is, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. In fact, we have a strict inequality if and only if a and b have different signs. Let's try to go over the proofs of these three statements. We'll begin by showing the first one. Let's choose an element x in f. According to axiom 01, that is the trichotomy law, we have three cases to consider. First, say that x is 0. By definition, the absolute value of x is 0 in this case. Let's say that x is positive. By definition, the absolute value of x is equal to x, so again, the absolute value of x is greater than 0 in this case. Now say that x is negative. By definition, the absolute value of x is negative x. Since negative x is positive whenever x is negative, we see that the absolute value of x is greater than 0 in this case as well. So staring at these three cases, we see indeed that the absolute value of x is greater than or equal to 0, where the absolute value is equal to 0 if and only if x itself is equal to 0. Let's focus on proving the second statement, that is that the absolute value of the product is the product of the absolute values. It turns out that we have 5 cases to consider in this case. Here, we're using the trichotomy law again to realize that a and b are either 0, positive, or negative. What if either a is 0 or b is 0? In this case, a times b is 0, and so staring at things, the absolute value of the product is equal to the product of the absolute values, which is just equal to 0. Next, let's say that both a and b are positive. In this case, the absolute value of a is just a, the absolute value of b is just b, and because the product of two positive numbers is also positive, the absolute value of a times b is just equal to a times b. So in this case, our identity still holds. Now we get to an interesting case where a is positive, yet b is negative. In this case, I'll let you read through the discussion here on the screen. If a is positive and b is negative, then the product a times b is also negative. So now we just have to be a little bit careful to make sure that the signs work out in the right way. So we would have to show that the absolute value of a times b is negative a times b, which we can write as a times negative b, which is the absolute value of a times the absolute value of b. For the fourth case, here we'll flip around to say, what if a is negative and b is positive? Well, case number 4 pretty much follows with the same argument as case number 3. Here, we would use the following phrase. This case follows mutatis mutandis from the same argument as in case number 3 with the roles of a and b interchange. This Latin phrase, mutatis mutandis, means having changed what needs to be changed. It's not the same as loss to generality, but it's pretty much like saying by a similar argument. For the last case, case number 5, let's say that a and b are negative. One shows that if a and b are negative, then the product a times b is positive. So it suffices to show that the absolute value of a times b, which is equal to a times b, is just equal to negative a times negative b, which is the absolute value of a times the absolute value of b. You can see the argument here on your screen. So this does indeed show statement number 2. We conclude now by showing statement number 3, that is the actual triangle inequality. The absolute value of the sum is less than or equal to the sum of the absolute values. Remember that we want to ask when we have an equality versus a strict inequality by looking at the signs of a and b. Just like before, we'll proceed using 5 cases. Let's first say that either a is 0 or b is 0. In this case, a plus b is equal to b, and so it's a matter of just simply showing that the absolute value of a plus b is equal to the absolute value of b, or absolute value of a, which is equal to the absolute value of a plus the absolute value of b. Let's consider case number 2, where both a and b are positive. In this case, the absolute value of a plus b is equal to a plus b. Remember before that if a and b are positive, then the sum is also positive. So this is equal to the absolute value of a plus the absolute value of b. Notice that a and b have the same sign in this case. Case number 3 asks when a is positive yet b is negative. In this case, we have to be a little bit careful. We actually have to look at 2 cases. What if the sum a plus b is positive, and what if the sum a plus b is negative? In either cases, we would find that the absolute value of a plus b is strictly less than the absolute value of a plus the absolute value of b. We'll let you read through the screen here to see exactly what's the argument to get these cases to work out. Case number 4 follows mutatis mutandis from case number 3. Before, we were assuming that a is positive, b is negative. Case number 4 assumes a is negative, b is positive. In the final cases, when both a and b are negative. Remember that if a and b are negative, then the sum a plus b should also be negative, and it's just a matter of working out the rest of the inequalities. For example, you would find that the absolute value of a plus b is negative, parentheses, a plus b, which is negative a plus negative b, which is the absolute value of a plus the absolute value of b. In this case, notice that a and b have the same signs, and again we have equality. So in all cases, we do find that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. In the 5 cases, we really only have a strict inequality when a times b is negative. That is, if, let's say, a is negative, b is positive, or a is positive, b is negative. Thanks for listening.